So in this video, we're going to go over the uncertainty of loads and load resistance factor design, which is really a means to account for these uncertainties in a structural design setting. But just as a brief recap, something to remember is that, when we're trying to determine if a structure can support its loads, we want to make sure that the demands on the structure are less than the capacity of those members. But one of the big challenges is, what is the size of those demands? Is it small? Is it large? How do we determine that? And, how do we deal with this uncertainty in this loading? So to illustrate this uncertainty of loading, let's think about the live load that could be applied to a structure. So you might have everything down to, no load onto it to a huge amount of live load, but in, kind of anything in between. And so if we take all of the possible iterations of different loading which could occur on a structure from live load, it will have some probability distribution, which is effectively a normal distribution. And so we can use this in order to, make a guess at, well, what do we use for design? Because we could use the zero, we could use the upper end, and if we use the upper end, we'd have lots of confidence that our structure would be okay. However, you might end up with very expensive structure and very lots and lots of material used. Conversely, if we went down at the lower end, we have a more efficient structure, but we might have more load go on than the structure can take, and that's not good. We'll have the structure fail. So you might think, well, maybe we use the median value or the mean value. The only challenge with that is that, well, it means that half of the time we're going to have more load applied to the structure than what we would design it to take the capacity for. Because remember, we're always going to come up with the capacity of the structure based upon the loading which is there. So a nice sort of middle ground which is used is that design codes around the world use this 5% chance of exceedance in 50 years. And so that means that over this assumed 50-year design life of a structure, you only have a 5% chance that you would ever see loading on that structure greater than its demand. So that seems like a nice sort of balance between making sure that we have, this little tiny bit of probability out here that we're going to be exceeding, while most of the time, 95% of the time, we know that we're going to be just fine and have more capacity than we have demands. And so with these uncertainties, probability distributions are all well and good for statisticians, but we're engineers. We need a tool which we can use in design. And this is not a terribly useful tool, even though it is very illustrative. So given the fact that, both the dead load and the live load, so you can think the imposed and permanent loads both have some uncertainty, and the fact that they might happen at the same time, they might happen at different times, we need this engineering tool to help account for this. And that tool is called load combinations. And so just show you a few examples here from the loadings code in New Zealand 1170.0. The load combinations we'd say is, we'll assume that if the dead load acts on its own, so the imposed load G, then we'll multiply by 1.35. So we'll increase its load by 35%, just to, again, account for the fact that we're not quite sure what our distribution would be and where we would land on that distribution. So we're just going to up the load just to be conservative because we don't want structures falling down. Similarly, if we have both dead load and live load, or, as 1170.0 calls it, permanent load and imposed load, well, we'll increase our permanent load by 20%, and then we'll add that to a 50% increase in the imposed load. And then that will be the load that we design our structure for. So you can see we're doing quite a big jump here. And what we want to do is that we've got all of these different load cases available in our loading standard. And then when we determine our capacity, we take whichever one provides the most demanding action. So the highest bending moment, the highest shear. And that's what we're going to say is going to govern the design, whatever loading combination governs the design. So for gravity only, it's typically going to be this 1.2 plus 1.5, 1.2G plus 1.5Q load combination. Just as another point to stop and discuss, it should be noted that we're only increasing our gravity load by 20% while we're increasing our imposed load by 50%. And this is really reflective that we've got more certainty in what our permanent load is going to be, because we know the size of our members, we know what we're going to fix onto a structure, but we've got a lot less certainty around, how many people might be there, what furnishings might get put on, and all those other things which are sort of out of the control of the structural engineer once the design is built. So to account for that and account for the greater uncertainty, we increase that load even further. So that's really our tool to deal with this uncertainty, is these load combinations and these load factors. And while we design, we also want to think, I've talked a little bit about we don't want structures to fail. We should really define failure and define some performance criteria. And those are what we call limit state design. And with this limit state design, again, a higher level thought on this is really the purpose is to make sure that we have more capacity than is demanded of the structure. Or another way to think about it is that our design strength of our structural element has more strength than what is brought to it from the design loads. And so if we go back to thinking about these limit states, what are the performance objectives? And it really comes down to this question, is my structure okay? Will it collapse? Will it bend too much? Will it be able to withstand fire? If someone's sitting on a desk on the floor, if someone runs by, will the floor vibrate? Will it move a lot in the wind? So these are these sort of performance objectives that we want to define for a building, and we will broadly lump those together in what we call these limit states. And with these limit states, this helps make sure that we have a some set criteria to design to, and then we can adjust the loading and the demands to be reflective of what the consequence of those failures are at these different limit states. And so with the limit states, we broadly have two here in New Zealand and also around the world. One is called the ultimate limit state, and the other one is called serviceability limit state. So ultimate limit state is probably where you'll spend most of your time when you're doing your analysis, and this is really making sure that the structure will stay up, and it's determining how will it fail. Will it fail because we've fractured material, so be it steel or timber? Have we yielded it? Is the element buckled either globally or a portion of it? Have we had a structure which has then been pushed over and we've got overturning? So this is really the ultimate limit state, is what we want to make sure the structure can withstand so that it is safe under to life and people using it. So it's to make sure that it's not going to collapse and not going to hurt anybody. Now, the serviceability limit state is our sort of day-to-day performance, and this is to make sure that the building performs in a way which is not, that makes it useful. But if we fail the serviceability limit state, the structure is not going to collapse, it's not going to hurt anybody, it will be annoying, and that would be like the floor deflects too much, and so, your pencil is always rolling off of your desk. You might have some cracking, and so that might then allow moisture to come in and you'll get corrosion of reinforcement or your steel. As I said before, your floor might vibrate too much. And so, again, with all of these, if we, quote unquote, fail a serviceability limit state, well, the building's not performing as well as it could, but no one is in danger. While our ultimate limit state, this is really in order to make sure that we maintain safety of the structure, be it the building or bridge or any other type of structure we would be doing. And so we want to check both of these. And if we say the structure has failed, if it doesn't meet the performance criteria of either one of these limit states. So again, coming back to this, purpose of design, we want to make sure that we've got, more capacity than we have demands. These design loads is this live and dead load, which we've already talked about. The way that we help ensure this is by really bumping up what the design loads are. And that's that, 5% probability of failure within 50 years. Now, for our design strength, what we want to do is also account for the fact that we've got some uncertainty in that design strength. We've already, sort of looked at how we deal with uncertainty in the loads. How do we deal with the uncertainty in the strength? And one of the ways to do that is to just see, well, where do these uncertainties come from? So if you're working with timber, well, it's a natural material. Depending upon how the tree grew or what tree you had or how fast it grew, it will have different strength. And there'll be some distribution of that, and there'll be a lot more variation in the properties of natural material like timber than you would a manufactured material like steel. But even within steel and concrete, you have some variability in the manufacturing process. You've got which can add into that additional uncertainty. And then the really big one is that construction practices and the realistic behavior on site, and the fact that not every member is 100% perfectly straight. There's some tolerance for that. All of that's going to add up to reducing down our capacities. And so we need to account for that in some form or fashion. And so just like with our design loads, we've got, all of these different uncertainties add up to some probability of what our actual strength of the member would be. And, as we discussed with the loads, one way to think about it is we could just choose what our, probable strength, our mean strength is. And when we assess a building, this is what we do. But for design of new buildings, we prefer to be conservative. And so what we do is we take what we call the nominal strength, or the characteristic strength, which again is this 5% lower bound. So we would, all material properties, there's a 95% chance that the strength of the material is larger than what is used for design. And for manufactured materials, obviously this bell curve is steeper and tighter because they want to make sure that they're not having to produce really strong materials out here and then sell them for a weak capacity. And so, but whether it's a manufactured material or a natural material, there'll be some distribution of strength. And we're going to use the lower end of that, because that's really what we're going to try to do is, again, bump up our loads and push down our capacity, because we want to be conservative, and that's because we don't want the structure to fail at that ultimate limit state where work safety is of critical importance. Well, then what we want to do, one way to think about making sure that your capacity is greater than your demand is you sort of overlay these two distributions of your strength and your demand. And, if you've somewhere over here and you've got more strength than, what your demand would be, you're safe. And so, but if we look at sort of this 5% probability, which we've used to, would be at the 95th percentile of loading and at the 5th percentile of strength, well, that actually gives us a 1 in 20% chance of, or 1 in 20 chance of the building failing. So it's a 5% chance every year that, something's bad is going to happen to the building. That's kind of high if expecting everyone goes into a building expecting it to just, stay up and be strong and stable and perform like it's supposed to. We take that for granted. When we go into a building, we're not expecting like, oh, well, we've got a 1 in 20 chance that the building's going to fail on me today. So because that level of performance is not acceptable, we also throw a further factor on to really sort of push down where this overlap is and really reduce down any probability that we're going to have failure at either the ultimate or the serviceability limit state. And we do that by throwing some factors on. So we have on the demand side, we have these load factors, which are all greater than 1. And so what we do is we take, whatever our design load is, we take this nominal load, which is this 95th percentile load, and we throw some factor on it. And that factor is always greater than 1, and that'll bump up the load. And for our strength, we reduce down our strength. And so for the strength that we use in design, we take this nominal 5th percentile strength, and we put some strength reduction factor on there. And that is always going to be less than 1. And so having a look at some of these load factors here, as I said, they're all going to bump up. We've seen some of these already. for at ultimate limit state and at serviceability limit state, you'll notice that we're using different factors. And the reason for that is because we have a different consequence of failure. So for the ultimate limit state, you'll see that we're really bumping up our dead load and our live load by 1.35 and 1.5, like we showed in an earlier slide. It's a pretty extreme factor that we're throwing on there, and that's really because we don't want our structure to collapse. We want it to be safe, and so we'll be really conservative and deal with the uncertainty that we have by putting on even higher load factors. However, at serviceability limit state, you can see that we're just basically taking for dead load, our load factor is 1.0, so we're just taking that nominal load, that 95th percentile load, and then for live load, we're actually reducing down, and this is because on the day-to-day performance of, say, a floor, it's unlikely that you're going to be at full occupancy. And so, if we want to make sure the floor is not deflecting too much or not vibrating too much, we assume that actually, most days, because the consequences that, the building just is a little bit annoying, we don't have to be nearly as conservative on that. And so we can take that reduction when we're doing the design. And we'll also find that, we will design for safety and then we will check the serviceability. Oftentimes the demands will force the capacity of an element at ultimate limit state to easily meet the serviceability limit state rules. And so just a little example of how these are applied, as we've showed before, for the ultimate limit state, the dead load will just add a 20% increase, and then for the live load, we'll add a 50% increase, and that is what our demand will be that we use for our calculations to design our structural element. And then for serviceability limit state, analogously, we're looking at, just a 1.0 factor multiplied by that dead load that we have coming out of our tables, or how we've calculated from, say, our self-weight. And then similarly with our live load, we just throw a 0.7 factor on there. So hopefully that, from the increasing the load size, it should look pretty straightforward. It's simply taking the loads you've calculated and then putting some factors on them and having some combination of those two. And then from the capacity side, really what we want is to reduce down what our material capacity is going to be based upon really what action it's going to see. So you can see that, concrete, whether it's in bending or in shear, because shear is a very brittle, sudden failure, we reduce down the capacity even more. Also, shear has a greater uncertainty, so we have to pay a bigger numerical penalty by only taking 3/4 of its sort of nominal strength, while flexure, we've got a bit more certainty, and the consequence of failure is not as big because it's a ductile failure mode, and so we only take a 15% reduction. And then you can see with structural steel, we've got a lot better handle on how steel behaves, so we only have to take a 10% reduction, and then on down the way. So how do we apply this in design? Well, first we select our nominal dead and live load. So we looked at that in the last video of how we can come to those. And then we multiply by our load factors and we combine those together. And then we will get what our demand is. And we denote this with a little asterisk. And so this S star, this could be whatever design action we're looking at. So if it's the axial force, it'll be N star. If it's the moment, it'll be M star. If it's the shear, it'll be V star. And then this is just effectively the terminology we use so that we know, and when we're communicating in our calculations, that the load that we're using here has already gone through these load factors. And then when we're doing our strength reduction, so we will take the nominal strength, which is called Sn, and then we use this phi factor, which we showed some examples in this slide here. And we simply make sure that the capacity side is bigger than the demand side. And that's really all that we're doing to deal with this uncertainty of load. It does effectively come down to some pretty simple and straightforward equations, and all to just say, because we don't know what's going to happen to our structure, but we want to ensure that it's going to be safe, we're going to be conservative, reduce down our capacity, increase the demands on there, and then do our design based upon that. And so that's really all we have to deal with the uncertainty of loads. So, thanks for watching.